In today's lesson, science and reading combine with the magical transformation of bread. This text is designed for a 5th grade reader, but I believe the information in this text could be good for any age level of reader, even adults, and any student at all could benefit from time with this reading and lesson. In this informational text that we will read, Marcus Wu describes the chemical changes involved in making bread, from its beginning ingredients to the final fluffy product. As you read, take notes on the changes that the dough and eventually bread goes through. The text and information in this video comes from Common Lit, and you can reach that by going to Common Lit in Google. It's a reading program for students and it is free. The Lexile level of this text is 820. If you wanted to print a copy of this later or go online and read it, you can find The Magical Transformation of Bread by Marcus Wu at Common Lit. You may eat your PB&J sandwich without even thinking about what's holding it together. But without bread, you won't have a sandwich. You'll just have a mess. To people from all around the world, bread is an important, familiar food. But it's also an amazing transformer. To turn into those soft, chewy, and delicious slices of bread, your loaf had to go through an extraordinary series of changes. So one of the words we're going to look at in this text is transformer. It's a noun. A transformer is a person or thing that changes or alters something else. So that's another word for you too, alters. Alters means to change. So it's an amazing transformer. An extraordinary series of changes, extraordinary. It means above and beyond, amazing. As we continue reading, focus on this question. How do you turn water and flour into dough? So the heading on this paragraph set is Who Needs Dough? You only need 4 ingredients to make bread: water, flour, salt, and yeast. Yeast is a type of microbe, a living organism too small to see. Flour is dry and powdery. It comes from ground up grains of wheat. And when you add water, the flour absorbs the liquid. The mixture forms clumps. If you continue mixing, you'll get a big, lumpy blob. As you knead it, stretch it, roll it, and flatten it, the blob soon becomes smooth, and you can turn it into almost any shape. You have turned flour and water into dough. This magical transformation requires proteins. Proteins are molecules found in all living things, from plants to people. There are 2 main types of proteins in flour: glutenins and gliadins. Together, gliadins and glutenins form a network of proteins called gluten, which gives bread its wonderful texture and shape. Glutenins are why dough is stretchy. When flour absorbs water, the water allows the glutenins to move around. And as you knead the dough, the glutenin and gliadin molecules start joining together, and they form a stretchy network like a net made out of rubber bands. So after reading this section, how do you turn water and flour into dough? Hopefully you were able to say you turn water and flour into dough by mixing and kneading it. And as we continue reading, you'll be able to answer the question too, what important thing kneading this dough does with those proteins. The more you knead, the stiffer and more rubbery the dough becomes. The classic example is to think about pizza dough. says Andrew Ross, a scientist at Oregon State University. He studies wheat and is also a baker. If you push it hard and try to spread it out into a disc, it fights back. But if you leave the dough alone, those networks relax. The other kind of protein, the gliadins, help dough flow and soften. Without gliadins, your dough would be like a rubber ball, and the resulting bread would be dense and hard. But without glutenins, your dough won't be able to hold its shape. It would spread out like a pancake. So both of those proteins, the glutenins and gliadins, are needed. Dense means closely packed together, so dense and hard. So how does kneading change the dough? Why do bakers knead the dough? It's something scientific they're doing with those proteins. Think about what the text says. We read that kneading the dough makes the proteins join and become stretchy. And we also read that the glutenins and the gliadins made the gluten. Let it rise. After kneading your dough, you must let it rest. It's time for the yeast to do its job. These tiny critters eat the sugar in the flour. As they eat, they produce gas called carbon dioxide. It's similar to how you exhale carbon dioxide when breathing. Remember, you breathe in oxygen and you breathe out carbon dioxide? The gas gets trapped inside the stretchy gluten network of the dough, and this forms air bubbles inside bread. The bubbles create a sponge-like structure that makes bread light and fluffy. Yeast also make different chemicals that give bread tasty flavors and smells. In sourdough bread, there are also microbes called bacteria. The bacteria produce interesting flavors, including a type of chemical called an acid, which can make the bread a little sour. Bread needs salt too. Salt strengthens dough and makes your bread taste good. It also helps prevent the yeast from producing too much carbon dioxide too fast. So you might think or heard of bacteria as something bad, but not all bacteria is bad. There are good bacteria and there are unhealthy bacteria, but these bacteria are helping make your bread. So what do the yeasts do? What does the text tell us? And you should have been able to say that yeast make the bread light and taste good. Perhaps you said that the yeast organisms, they're eating the sugars in the flour. And perhaps you said that that was leading to carbon dioxide. And remember, carbon is C on the periodic table of elements, and oxygen is O. So it is a carbon and two oxygens. That's why it's CO2, carbon dioxide. So there's a little model of what's going on. And H2O, you see that there, yeast plus flour plus sugar plus H2O. That is the chemical element for water. Into the oven. When your dough has the perfect balance of stretchy gluten and air bubbles from the yeast, it's time to bake. Baking is one of the most fascinating transformations in cooking, Ross says. You put a lump of dough in an oven and a loaf of bread comes out. During baking, a lot of chemical reactions are happening. As the dough heats up, the yeast becomes more active and makes more carbon dioxide. The gas bubbles also expand like lots of tiny balloons, forcing the dough to rise even more. But when the dough gets hot enough, the yeast and bacteria die. Their job is done. Flour contains starch. Starch is made up of sugars, which provide energy for people who eat the bread. In the oven, as the starch cooks, it pulls water from the gluten. Without water, the gluten becomes stiff, forming the structure of the bread. The starch absorbs the water It expands, becoming soft and moist. On the outside of the dough, the crust starts to form. Heat causes a series of chemical reactions with the sugars and other compounds in the dough. They are known as Maillard reactions, and they are the same reactions that turn food brown during grilling, frying, and roasting. The dough hardens and becomes crunchy and crackly. It turns brown and creates toasty flavors that taste and smell delicious. So a lot is happening in that heating process. You read the word compounds, and in the text it said there's chemical reactions with the sugars and other compounds in the dough. A compound is a combination of ingredients. So when you compound something, you're putting things together. So what happens as the bread cooks? Covered a few things in here. How could you sum that up? What is happening as the bread cooks? And you should have been able to summarize that as the bread cooks, it expands and becomes hard on the outside. And you understood that that was part of another chemical reaction. You know that more carbon dioxide is being formed and more bubbles are being formed, and the bread is getting lighter and rising. And while at the same time, a chemical reaction is happening to turn the outer layer brown and more crispier. Staleness happens. Even after it comes out of the oven, a loaf of bread keeps changing. As soon as it starts to cool, it starts getting stale. It will slowly harden and won't taste as good. The bread seems like it's drying out, but what causes staleness isn't water loss. One part of starch is a molecule called amylopectin. It has a lot of branches like a tree. When you take the bread out of the oven, the amylopectin molecules start to tie together, forming crystals. Water gets trapped inside the crystals, and after a few days, so much the amylopectin has turned into crystals that the bread becomes hard and seems dry. To make this stale bread more appealing, it's best to put it in the oven or toaster. The heat unwinds the amylopectin, letting out the water. It's no longer a crystal. The bread becomes softer and moister again. Over time, though, the bread loses flavor and aromas, so even if you can soften it again, it may not be as tasty as it once was. Still, it's probably good enough for another PB&J. And that might explain why sometimes you have pizza and the crust gets harder and it's not as soft when you had originally ordered it, made it, or it had been delivered. But if you heat it up in the microwave, or if you put it in the oven for a little bit, you'll notice that the bread or the crust starts to get a little bit soft again. And so that's happening because of the amylopectin molecules that were tied together and crystallizing, and then letting some of that water out to make it moister and soft again. So why does bread become stale after it starts to cool? That's an interesting question that was answered in this text. Bread becomes stale because it has molecules that start to crystallize. And it talked about those molecules being like tree branches. And you can see between the fresh bread and the stale bread how they are forming closer together. And so they're crystallizing. And then you see the one arrow about reheating, how you can release that water from those crystal states and then make the bread more fresh again. So thinking about the text that we just read, what is the central idea? Remember the central idea of the text, especially a nonfiction text. We also refer to it as the main idea, so it's the main thing the author wants to tell us. If we're trying to sum up in a sentence and say, I think this is the main thing that the author is trying to get across to me as a reader, what would it be? That A, bread is difficult to make but important to humans' diets. That B, bread is better over time as the ingredients continue to interact. That C, bread is made and becomes stale through several chemical reactions? Or D, bread is made through several chemical reactions that scientists do not understand? What do you think the author is trying to tell us? What's the central idea? And hopefully you said C, that bread is made and becomes stale through several chemical reactions. The author really wants us to know the science or the chemistry behind this bread, from putting the ingredients together, kneading it, and then baking it, and then it becoming stale over time, and how all of those things are working together in bread, how the science is involved. Sometimes as a student, you are asked to support why you think the central idea is what it is. So what would best support, what quote from the text supports our answer to A? That the author really wanted us to understand that the chemical reactions are occurring as an important aspect in bread. Would it be A, you only need 4 ingredients to make bread: water, flour, salt, and yeast? B, you put a lump of dough in an oven and a loaf of bread comes out? C, heat causes a series of chemical reactions with the sugars and other compounds in the dough? Or D, to make stale bread more appealing, it's best to put it in the oven or toaster? Now, these answers are all just one aspect of the whole process, but which quote could support that as a central idea? It wouldn't be the only supporting detail, of course, but which one of these would be one of the best ones? And so B, C, and D are all about the process, but which one do you think is the best support for the central idea? If you said heat causes a series of chemical reactions with the sugars and other compounds in the dough, then you were correct. B and D are part of the process, but really what gave me the best support was those chemical reactions. I really think that that is supporting what the author is trying to tell us, that the making of bread happens through a series of chemical reactions from the beginning even to the process of becoming stale. Okay, here's another question for you. How are the flour proteins, glutenins, and gliadins important in making bread? A, they give bread its taste. B, they kill bad bacteria in bread. C, they make dough stretchy and soft. And D, they cause dough to release gases and rise. What do you remember reading about those proteins? I believe we read that in the section about kneading the dough. And the answer is they make dough stretchy and soft. When you're kneading it, you are putting those proteins together and they're working in unison to form your dough. Here's a reference back to the text. This magical transformation requires proteins. Proteins and molecules found in all living things, from plants to people. There are 2 main types of proteins in flour, glutenins and gliadins. Together, gliadins and glutenins form a network of proteins called gluten, which gives bread its wonderful texture and shape. This author had a process in writing about this information, and you are oftentimes an author too, and you've got to think about how you're going to organize your writing. So how did this author organize the information in the text? How did the author get the central idea across to us? A, by discussing different types of bread. B, by describing the steps to make bread. C, by describing different ways to make bread. Or D, by discussing his own experiences making bread. And the answer is B, by describing the steps to make bread. Heading titles in a text can help us too. So the author did put those titles there about kneading the dough and then baking the bread and then it becoming stale. So the headings on paragraphs can help us as well understand organization. Sometimes you might be asked questions about text, like what is the connection between heat and the transformation of bread? And if I was asked that question, and especially maybe to write about it, I would definitely use my heading titles to go back. So where it was talking about baking the bread in the oven, that's where I would go to because it has the word heat there. And an excerpt from that paragraph is, during baking, a lot of chemical reactions are happening. As the dough heats up, the yeast becomes more active and makes more carbon dioxide. The gas bubbles also expand like lots of tiny balloons, forcing the dough to rise even more. So this piece of text evidence will help me answer that question, what's the connection between heat and the transformation? It's telling me what heating up that bread does. There was also other information in that paragraph, but this will give me enough to answer that question. And when I am responding in writing, I always would like to restate the question so my reader understands what I'm writing about. I would like to use some text evidence, so maybe to say, has the text states, but I don't want to just copy down. I want to explain in my own words as well. There is a connection between heat and transformation of bread. So I restated what was being asked of me. The text states that as the dough heats up, the yeast becomes more active and makes more carbon dioxide. There's my text evidence. I'm going to explain that a little bit in my own words. The carbon dioxide bubbles make the bread rise, and the heat transforms the dough into bread that can be eaten. So there's a way to answer text questions. Okay, here is a video from a TED Ed, and it's a media connection, so you can learn in just a different way. Other than reading about it, you can view something now and get some more information about the things that we just read.
In a time-lapse video, it looks like a monster coming alive. For a moment, it sits there innocuously. Then, ripples move across its surface. It bulges outwards, bursting with weird boils. It triples in volume. Its color darkens ominously, and its surface hardens into an alien topography of peaks and craters. Then the kitchen timer dings. Your cookie is ready. What happened inside that oven? Don't let the apron deceive you. Bakers are mad scientists. When you slide the pan into the oven, you're setting off a series of chemical reactions that transform one substance, dough, into another, cookies. When the dough reaches 92 degrees Fahrenheit, the butter inside melts, causing the dough to start spreading out. Butter is an emulsion, or mixture of two substances that don't want to stay together. In this case, water and fat, along with some dairy solids that help hold them together. As the butter melts, its trapped water is released, and as the cookie gets hotter, the water expands into steam. It pushes against the dough from the inside, trying to escape through the cookie walls, like Ridley Scott's chest-bursting alien. Your eggs may have been home to squirming salmonella bacteria. An estimated 142,000 Americans are infected this way each year. Though salmonella can live for weeks outside a living body, and even survive freezing, 136 degrees is too hot for them. When your dough reaches that temperature, they die off. You'll live to test your fate with the bite of raw dough you sneak from your next batch. At 144 degrees, changes begin in the proteins, which come mostly from the eggs in your dough. Eggs are composed of dozens of different kinds of proteins, each sensitive to a different temperature. In an egg fresh from the hen, these proteins look like coiled up balls of string. When they're exposed to heat energy, the protein strings unfold and get tangled up with their neighbors. This linked structure makes the runny egg nearly solid, giving substance to squishy dough. Water boils away at 212 degrees, so like mud baking in the sun, your cookie gets dried out and it stiffens. Cracks spread across its surface. The steam that was bubbling inside evaporates, leaving behind airy pockets that make the cookie light and flaky. Helping this along is your leavening agent, sodium bicarbonate, or baking soda. The sodium bicarbonate reacts with acids in the dough to create carbon dioxide gas, which makes airy pockets in your cookie. Now it's nearly ready for a refreshing dunk in a cool glass of milk. One of science's tastiest reactions occurs at 310 degrees. This is the temperature for Maillard reactions. Maillard reactions result when proteins and sugars break down and rearrange themselves, forming ring-like structures, which reflect light in a way that gives foods like Thanksgiving turkey and hamburgers their distinctive, rich brown color. As this reaction occurs, it produces a range of flavor and aroma compounds, which also react with each other, forming even more complex tastes and smells. Caramelization is the last reaction to take place inside your cookie. Caramelization is what happens when sugar molecules break down under high heat, forming the sweet, nutty, and slightly bitter flavor compounds that define, well, caramel. And in fact, if your recipe calls for a 350-degree oven, it'll never happen, since caramelization starts at 356 degrees. If your ideal cookie is barely browned, like a Northeasterner on a beach vacation, you could have set your oven to 310 degrees. If you like your cookies to have a nice tan, crank up the heat. Caramelization continues up to 390 degrees. And here's another trick. You don't need that kitchen timer. Your nose is a sensitive scientific instrument. When you smell the nutty, toasty aromas of the Maillard reaction and caramelization, your cookies are ready. Grab your glass of milk, put your feet up, and reflect that science can be pretty sweet.
I hope you enjoyed this lesson and learned a little bit more about science and reviewed some scientific things that you may have already known, and also used text to learn that information through, as well as media. So you watched a video that had some of those same aspects that you learned about bread, but you learned about baking another substance, yummy cookies. Thanks for joining in.